Okay, thank you very much for the invitations. Thank you, Franz, Marcus, and Hans for organizing this nice meeting. The last time I was here was 20 years ago, and a fantastic semester that Hans organized. It was the time of wavelength and time frequency was exploding, so I have very good memories of this time. So I don't know how much this area match with come to this meeting in quantum harmonic analysis. So, but I hope that maybe somebody found an application in quantum harmonic analysis. I was actually thinking to put some quantum over there, quantum orbits or something like that. But I don't know if this is work. Okay, so this is a joint work with three very smart students. Now they're postdocs. Alejandra Aguilera, Venezuela. She made a magister in Venezuela and then a PhD, and now is a postdoc in Buenos Aires. And then Felipe Negreira is also a postdoc in Buenos Aires. He made the PhD in Bordeaux. And Victoria Paternostro is, some of you know her. She's a professor at the University of Buenos Aires. She made the PhD in Buenos Aires and then went to Berlin with Dieter Coutinho for the postdoc. Okay, so just to avoid any confusion, that's the object of this talk, to answer this question. So we have a Hilbert space. All the Hilbert spaces in this talk are going to be separable and complex. And we have a bounded operator T. And the question is whether there exists in the space a collection of vectors, most countable, that the iteration, the orbitals of the operator in these vectors, the union of these orbits form a frame of the space. That's the simple question. So I want to give a motivation why we are doing that. Yeah? So imagine you have a signal f, and the typical scheme in sampling theory is just to have a collection of functions and make some measurement with this collection. And from this information, you want to reconstruct the function. And we know that this is only possible if this collection of functions is a frame, form a frame of a space. So the idea here is that you assume that there are insufficient functions to reconstruct the signal f. We don't have enough information to reconstruct f. So you can imagine that the function f, the function g, when you make the measurement, are sensors. Because of that, it's very expensive or whatever other reason, you have few of them and you cannot get enough information. But so we assume that we cannot reconstruct it completely, the function, under this condition. But we assume that the function evolves in time under some evolving operator, t. Then the idea is what's happening after a unit of time, I activate again the sensors and get new measurement, but not from f, but from t of f. So we'll be able with this new information to reconstruct f now. So you can keep doing that until you get the necessary information. So this is an idea that has Martin Betterly and his team. He was an engineer from Switzerland. Some of you probably know him. I think he was thinking in the heat equation. We have the initial condition, and they want to know the initial condition to predict the whole evolution. And so we start to look at this problem with Akran, Ursula, and a student of Akran some time ago, and then we realized a simple fact. I mean, we want we sample the powers of T applied to F, and we sample with the function, with the collection of functions. But just a simple observation that you can put T on the other side as with a joint, tell you that the necessary and sufficient condition to recover F is that this iteration of T adjoint in Gj has to be a frame. So this changed the problem to a problem of operator theory. Now we have to look at this new problem that has nothing to do with signals. Okay, that's given an operator when the iteration have form a frame. Okay, so we start to look at that, and we start the easier case. This is the diagonal operator, and then end up looking at the normal operator. And the good thing for normal operator, we have the spectral theorem. So the multiplication by the variable, and then we can do something. And the theorem we got is very peculiar because in general, we're very hard to get a frame with this normal operator. For example, there are not exist bases. We cannot generate bases. It's a problem of minimality and completeness. But under certain very particular conditions, we can get frames. And the conditions are that the operator has to be diagonal and have a basis of eigenvectors, and the eigenvalues has to be in the unit disk, and the absolute value goes to 1 to the boundary. And also, and that's very surprising for us, is that they have to satisfy this condition. This condition says, but several things, but this was given by Cabrelli and says that the sequence of this complex number has to be an interpolation sequence in the Hatter space. This was, and also, it was their thought it has to be separated, informally separated in the hyperbolic distance. So, in that case, we have frames. So let me finish. This is just for if you iterate just one function, one vector. We extended other people for several finite number of functions, and I don't want to spend too much time, but there was a series of papers, and that all these people, some papers and some other papers, contribute to get the final result that is for finite number of generations. Okay. So general operators now. So here what we have is, I need some definitions. Assume an operator, bounded operator T we say that it's strongly stable if this happens. This means that the Tn of any function f goes to 0 in the strong operator topology. Second, T has to be, T is a contraction if the operator norm of C is less or equal than 1. And when this is known, two operators, we say that the two operators are similar. There exists a bounded invertible operator such that L1 is just maybe intertwining with between L1 and L2. So the theorem we have is that if T is boundary operator, then it has a frame of iteration if and only if T is similar to a contraction, yes. And T star is strongly stable. So these two conditions are necessary and sufficient. For example, an unitary operator is never has a frame of iteration because it's not strongly stable. Okay? The joint is also unitary. I have not one, so I will not go to zero. And the easy calculation shows also that any compact operator also doesn't have a frame of iteration. A hypercycle operator doesn't have a frame of iteration. Yes. Sorry? Yes. Always. Yeah. The finite dimensional case we solve it independent and it's very simple. Sorry, I have thank you for. So what happened with Parseval's frame when we want to see? Okay, if you have a Parseval frame of iteration, have to satisfy the condition of that we already gave because it's a frame, but you need something else, and in place to be similar to a contraction, has to be a contraction. Okay, so that's this we got it recently, and that's it. This is all we need. So we can go home now. But the thing is, what is more interesting is the methodology that to get this result. We use a lot of things that was already known, but I want to go a little bit over that. So we need some definitions. So assume K is a general any Hilbert space. So we notate that H2 of K, the Hardy space functions valued in K, and that are that have analytic in some you can say analytic have this series of powers. Actually, these are Fourier coefficient, positive Fourier coefficient, and these coefficients that are in the Hilbert space have to sum finite, and the multiplicity of the Hardy space, this Hardy space, is K. So this is going to be the main object that we are going to use. So here, the operator, the typical operator in the Hardy space is a sheaf operator. So in this context, the sheaf operator can be defined as just a multiplication by the variable. Yes? The functions here are defined in the torus. Okay? It could be defined in the open disk, but we use the torus. Okay? So just to make it more clear, if you have a series like this, the sheaf remove the constant function and shift it the whole thing to the right. And the joint of the sheaf operator have this form. Recall that f of 0 is just a constant. You remove the constant, and then you get this one. So one thing that I want you to take from here is that when you apply the adjoint of the sheaf, you lose the first element in the sequence. So this means that when you iterate this operator, this has to go to 0. So this is a sequence that has this property of the norm be in L2. So the iteration of a start in NAF have to go to 0. So it's a stronger stable. And well, this was an observation we need later. So other operator that But first, let's define these spaces. A subspace of H2 of K is S invariant if it's invariant under the sheaf operator. Okay. So, and the orthogonal complement of invariant subspace is called a model space. It's called a model space, and it's defined because it's invariant. M is invariant under S, so N is invariant under S star. So this is called a model space because it has been used as a model for several people for study contractions, yes, in Hilbert space. So, and the other operator that we need is the compression of the sheaf. The sheaf in N is not invariant under the sheaf, but if you apply the sheaf and then project it back to the model space, then you get an operator that is called the compression of the sheaf. So let me tell you that the sheaf invariant spaces of this generality have been studied for Turning first for dimension 1, for multiplicity 1, and then Lux make it for multiplicity, final multiplicity, and Halmos for infinite multiplicity. The proof of Halmos is very nice. You have the chance to read it. I really recommend it. Okay? A rainy Sunday afternoon, you can have it. So, what happens with the compression of the sheaf in any model? If you take an orthonormal basis of K, that is the basis of the Hardy space, K can be seen inside the Hardy space as a constant function. So you take an orthonormal basis and you project it over the model and iterate the compression of the sheaf over these projections, you get the partial frame of the model. So iteration of the compression of the sheaf is a partial frame. So they have to satisfy the condition of the theorem. Okay, the compression of the sheaf is a contraction, is adjoint, is a star that is goes to zero, it's a strongly stable. It satisfies the condition. So we start in the other way. We start here and then we move to the general Hilbert space. So let me explain which is the general idea. You have an operator T in a Hilbert space. You want to prove that you have a frame with iteration or doesn't have. Then what do you do? So it's too general, the Hilbert space. So what we do is just look at the functional model. Okay? We look at the model and we look at this operator, the compression of the sheaf in that model. We make the proof there, and then we need to have a way to go back to our Hilbert space. So we use two ways to do that. One is an observation of Ole Christensen and Hazarahad and Phillips, that they observe that you have a frame of iteration in a Hilbert space, and you take the synthesis operator, that define it in the Hardy space in place in the sequence space that applies the Fourier transform. Then the kernel of the synthesis operator is invariant under the sheaf. So if you restring the synthesis operator to the orthogonal complement, you have an isomorphism with the Hilbert space, and then everything what happened in the model space goes to the model space goes to the Hilbert space. That's one way to go and back. We generalize this with Daniel Suarez, that is an expert in complex analysis, and we could do that in a different way for several functions. So the other way to obtain an isomorphism, in this case a unitary equivalence between a Hilbert space and a model, is using a model of Rota. This is of the 60s. Rota make a map between the model space and the Hilbert space. And then this map was an isomorphy, but was refined later by the branch and Ronjak. It was very peculiar because they published a paper in the, and actually it was an advanced research announcement where they say that they proved the famous conjecture on the invariant subspace. And there was a gap in the paper, but they make a refinement that is very useful. So just to say 2 words on this, it says that T is a bundle operator that is a contraction and strongly stable. Then T is entirely equivalent to the compression of the sheaf in some model. And let me say just 2 words about this model. Which one is this model? So this is called the defect operator. This is a self-adjoint operator. And the image, the closure of the image of the space under this operator is called the defect space. So we take the Hilbert space, the Hardy space H2, whose base is the defect space, and make this map from H to H2 of this chart in this form. Look at this work. You take an X in the Hilbert space, make the orbit of this X, apply D, this D is what makes the thing unitary, and then put it in the Hardy space multiplied by Cn. So this lives here clearly, and it's unitary, and the image is a model space. So that's the other way to go back and forth from the Hilbert space. And we use this for Parseval frames. So, have just a few minutes. We wanted to study now we know which operators have frame of iteration, and we know how to construct. I didn't say how, but the way is just taking an autonomous basis in the base Hilbert space of the Hardy space, and then project it on the model, and then iterate the compression of the sheet. We want to know which is the minimum number of generators you need to get the frame of iteration. And then we define the index that has the definition of the index is the minimum of these such that there exists D generators. Okay? We say that the index is 0 if T doesn't have a frame of iteration, and it's infinite if it doesn't have a finite one, but have one. So the same definition for Parseval frame, but requiring that it's Parseval. So if jump here, we got that T is a contraction and it's strongly stable, so the index is positive, then it's exactly the dimension of the effect space. This requires some work, but you can get it from this Rota model. Sorry? Could be finite, yes. Yeah. Could be finite, but could be infinite also. Yeah. So here is how the general construction. You have this unitary operator. You take an orthonormal basis. You project it in the model. You just iterate the compression of the sheaf. You apply now the unitary operator, and you get a Parseval frame in the Hilbert space. So this optimal, I didn't say what it is, but optimal means that it's the minimum possible. We are almost done. I want to say that that for the question of Hans, in the operator that for the normal operator that I put in the first slide, the index of operator is 1, because this theorem says that you can generate the frame with one vector. But if you want parseval's, you need infinite vectors. So this is really annoying. Let me jump this. And just to say, this last minute, 2 words about when we want to study now the following problem. We have T, and if it's strongly contraction, and if it's strongly stable, then you have a frame of iteration. But if T is a contraction, T star also is a contraction. So assume now that T star is also strongly stable. So this is called disjoint strong stability. And we want to study this because we want to get frames of iteration for T and for T star. We say, well, we have to study the joint stability, we have to go to the model, because you have much structure to do that. And we discovered something that was very surprising for us. We have to use the dilation theory of Nagy Foyas and these people. And the relation is that there was a property in the invariant spaces, shift invariant spaces, in hard spaces, that studied Helson in the 60s. Everybody in this moment in operator theory was trying to solve the invariant subspace problem. And that was called full range. And so the definition of full range, I think I put it there. You take in shift invariant space, you take the for 6C, you take the image for all the functions in the invariant. This has to be the whole space, base space, the hard. This full range. It is incredible. This property is exactly equivalent to joint stability. I will stop here. I have more things to say, but I don't want to go through the hour. So thank you very much.